This conference will now be recorded.
Very good evening, students. Today we'll be learning very interesting thing related to electric equipotential surface, electric dipole, electric field, and potential produced by an electric dipole, and torque and force on a dipole, potential energy, etc. Okay. So first, let us learn what is called equipotential surface. So as you can guess from this word itself, equipotential. Equipotential means a surface everywhere of which the potential electric potential will be zero. Electric potential will be equal. So an equipotential surface is a three-dimensional surface on which the electric potential is the same at every point on it. Okay, so you might be thinking, what is this? Okay, so let me just take a simple example. Suppose I have a positive charge, okay, positive point charge Q. If I ask what is the potential at a distance r, we know it has a fixed value, so Q by 4 pi epsilon naught r. If I consider a spherical surface, of radius r, keeping this positive charge Q at the center, then look, the potential on this spherical surface at each point on this spherical surface is same, because this distance is same. Okay, this distance is same and charge is anyway the same, and these are the constant. So I can get a surface. This is three-dimensional surface, as you can understand, a spherical surface. So this is three-dimensional surface, and you can see at each point on this surface the electric potential is same. Okay, that is what is called equipotential surface. So equipotential surface is a three-dimensional surface on which the electric potential V is the same at every point on it. So this is equipotential surface. Now, equipotential surface has few characteristics. Let us just learn one by one. First thing is that zero potential difference between any 2 points. Suppose I have plain equipotential surface. I'll tell you when the surface, like how the equipotential surface will look like for which cases. So suppose equipotential surface, this is equipotential surface. That means if I take a point here A, if I take another point B here, so both the points, see, VA will be equal to VB equal to V, that has the same potential everywhere. So what is the potential difference? So VB minus VA will be 0, isn't it? So this is what it is. So potential difference between any 2 points will be 0. So if potential difference is 0, then I don't have to work, or I don't have to do any work while taking a charge, point positive charge. Suppose I'm taking a positive charge from A to B. So A to B, I'm taking a charge from A to B. Okay, A to B. So what will be the work done in this case? excuse me. So I was discussing there will be no work done if we take one charge Q from A to B. Okay, since there is no potential difference, actually work done is Q into V. Okay, Q into V. If there is no potential difference itself, in this case VAB. So if there is no difference in the potential, so I don't have to do any, or I don't have to perform any work to move a charge from one point to another. So no work done by the electric force when test charge is moved along the surface. So two equipotential surfaces can never intersect each other. So this is another point of why, because just like electric field lines or magnetic field lines, see what we had understand. So what we had understood, equipotential surfaces, like see this, these are electric field lines. So if they intersect like this, so I can get two directions of electric field, right? One is this one, this is second one. Similarly, if equipotential surfaces intersect each other, then there will be two different directions. Or see, equipotential surface means what? A particular potential will be there. See, suppose in this case it is V everywhere. So another potential surface will have some other potential, electric potential. Suppose this one, this will have V prime maybe. So if they intersect each other, then I can have a point where there will be two different potential, but that is not possible. And also we can have different field, that is not possible. So at the same point there should not be, or I should say there must not be two different potential. So that's why electric, see this equipotential surfaces will be always parallel to each other. Okay, I'll tell you when I discuss different types of equipotential surfaces. Like see, in this case these are planar equipotential surfaces. They will be actually sorry, if I take some planar equipotential surfaces, so equipotential surfaces will be parallel to each other always. I take another, okay, sorry, like this. Okay, potential surfaces will be parallel to each other. So this is suppose the some direction this way. Okay, so this is one surface, another surface is this one. So they have different potential V1, V2. Okay, so these surfaces will not intersect each other. All right. Now I have another point, that is electric field must be perpendicular to the surface at every point. Okay, so here I'll tell you, or we can prove it how or why electric field must be perpendicular to the equipotential surface at each point. Why do you think that this should be, the electric field should be, so electric field must be perpendicular to the surface? Why do you think this? See, we have already seen that work done by electric field will be zero. So work done by electric field zero means what? I can say electric field is a vector, and the displacement along the surface is C zero. If this is zero, what does this mean? That displacement is there. So displacement cannot be zero. Electric field cannot be zero. What is the possibility? That electric field must be perpendicular to the surface, isn't it? Must be perpendicular to the displacement. First of all, displacement. And displacement, how we go? See, if I have parallel parallel equipotential surfaces. Equipotential surfaces like this, and this. These are parallel equipotential surfaces. Oh, I'm sorry. Like this. If I have parallel equipotential surfaces, so in this case, the electric field. See how you take the displacement through this. We go like this. Okay, displacement will be always perpendicular to the surface. Okay, see, sorry, electric field should be always perpendicular to the electric field. So displacement may be here like this. Okay, along the surface. Displacement goes like this along the surface. In this case itself, you can understand. Okay, let me just draw once again. I'm just by default taking planar surface, but we can have concentric circles, spheres, spherical surfaces, and concentric cylindrical surfaces as well. So if this is the thing, see, if this is vertical standing, so the displacement will occur along the surfaces, okay, along the surface, and electric field will be like this in this direction. So it is perpendicular, okay, perpendicular. Why? Because this work done is zero. Work done due to electric field at any point, okay, will be zero. So that's why from that corollary we can just say that the electric field will be always perpendicular to the displacement. Okay, perpendicular to the displacement, and displacement always occurs along the surface. Okay, along the surface it occurs. All right. Okay. So just go to, see here. I'll show you. This is suppose a point charge, point positive charges. You know how electric field lines are. See, electric field lines are just diverging. Okay, so they are actually pointing outwards. Okay, and see, this is equipotential surfaces. Surfaces due to a positive point charge. Positive point charge. Okay, so in this case you can understand. See, if I draw concentric spherical surfaces at different distances, see, for example, this spherical surface, this has got 40-volt potential at each point on the surface. The second one, see, second one, little bit larger radius of this. Okay, so this surface has got spherical surface. This has got another constant potential, that is uh, 30 volt. At each point on this surface will be 30 volt. Similarly, for this one, this will have 20 volt. This one will have 10 volt. So as you go away, in this case, the potential is decreasing. Anyway, but what I am trying to say is that for a point charges, equipotential surfaces, point charges, equipotential surfaces will be concentric spherical surfaces or sphere, concentric sphere. So this is actually concentric sphere, concentric spheres. Okay, or spherical surfaces we can write. So what about this? See, in case of uniform electric field, uniform electric field. In case of uniform electric field, and uniform electric field is always denoted by equidistant parallel lines. Okay, and their equipotential surfaces will be always planar. Okay, plane surfaces, as I was drawing that time, like this, plane surfaces. Okay, this will be plane surfaces. Okay, like this. Okay, so this dotted line are saying that planar surface, plane. plane parallel planes. Okay. Equipotential surface for uniform field will be plane surfaces. And if it is see in this case actually it is not a uniform electric field, I can say, because I'm sorry, no, it is for uniform electric field, uniform E, uniform E, because see this distance, this distance are same. When the interplanar spacing is same, then uniform electric field. Suppose interplanar spacing is not same, then it is not a uniform field. See, in case of line charges, so point charges we get concentric circles or sorry, concentric spherical cell or sphere. But in case of line charges, so you can guess that the equipotential surfaces will be concentric cylindrical surfaces. Okay, concentric cylindrical surfaces like this. Okay, concentric surfaces, cylindrical surfaces. All right. So in case of line charges, this is line charge, line charge, concentric, concentric cylindrical surfaces. Okay. All right. So in this case, uniform electric field. In case of uniform electric field, there will be equidistant. See, equidistant parallel planes. All right. So sometimes there could be a question. Okay, first of all, let me tell you, while drawing the electric, yeah, see this equipotential surfaces, we should keep in mind that perpendicular. See, electric field will be perpendicular. Electric field lines will be perpendicular at each place, okay, on the surface. See, in this case, electric field line, it is actually perpendicular to this, okay, perpendicular to this, and this point, okay. In case of this uniform electric field also, you can see the electric field lines are always perpendicular to the equipotential surfaces, okay, at each point. And similarly, see how you draw electric field lines in case of cylindrical or linear charge distribution. This will be like this, okay, radially outward like this, and this will be always perpendicular to the cylindrical surfaces or curved surface. See, field lines always will be flowing from higher potential to lower potential. That's why, see, sometimes this electric field lines you have to draw. Suppose these are various plane surfaces, so you need to draw the electric field lines. So how do you draw? You have to give the arrow for the electric field lines or electric field in which direction potential is decreasing. Potential is decreasing because we know electric field is equal to minus dVdr. dVdr. So what does this mean? Electric field increases in the direction. In the direction, not increases, I should say. Electric field line has a direction. Okay, it is directed from a lower potential to the higher potential direction always. So that's why 30 to 40, sorry, 40 to 30, 30 to 20. In this direction, the electric field lines are given. Now, in case of non-uniform, so equipotential surface for surfaces for a non-uniform electric field. Electric field. So, see, in this case, let us take two cases, first one and second one. See here, nature of equipotential surfaces in electric field increasing in the z-axis. If the electric field is increasing in the z direction, see we know E is equal to dV by dx. So in which direction electric field will increase? The direction in which actually, so if the electric field increases, what happens actually? The space between the spacing between the equipotential surfaces like this. See the equipotential surface of 1, 2, and 3. See, equipotential surface between distance between equipotential surfaces 1 and 2. This distance is much larger than D2. Okay, this is D1 and this is D2. So where the electric field is stronger, whether here in between this or electric field is stronger here. This can be obtained from here itself. See the potential surface, say dV. There is a change in the potential dV. So V1 and V2, I can say V3 this one, and this is V2. Say V2. So what is the dV? dV is V3 minus V2. This is obtained. What is dx? dx is the distance. Okay, between the planes. So this is d. Okay, so this d. So this is actually electric field. Okay, this is the electric field. So V3 minus V2 by d. So if this one is decreasing, then only electric field will be increasing, isn't it? If this, so if the electric field is increasing in certain direction, the equipotential surfaces will be closer and closer and closer. Okay, closer to see this D1 is actually greater than D2 here, right? So electric field is increasing in the Z direction. But what about this one? See, in this case, D1 is equal to D2. That means it is, see, everywhere, see, this distance is D1, this distance is D2. They looks like the same. So D1 is equal to D2. Therefore, here, see, this is uniform electric field is existing along the Z direction, but electric field is not changing. This is a constant uniform electric field. Okay, constant uniform electric field. So this is one fundamental thing to understand. Okay, I think with this, we have learned almost all the concepts from the equipotential surfaces. Now we'll learn about electric dipole and related physics. Let us go to that topic. So what is an electric dipole? An electric dipole is actually a pair of charges separated by a small distance. So a pair of equal and opposite charges, suppose plus or minus q, that are separated by a fixed distance, fixed and small also. This distance is small. If it is very, very large, then it will not constitute an electric dipole. So small and fixed distance, this distance will not vary at any cost. This distance will be fixed, known as electric dipole. So here you can see this is minus charge and this is plus q. So both are separated by a distance 2a, and you know this 2a is actually very, very small, smaller distance. So this is electric dipole, and see, we always define a parameter called electric dipole moment related to electric dipole moment. So what is this electric dipole moment? Electric dipole moment is always defined as, so it is denoted by P, and it is a vector quantity, and it is always defined as one of the, say, magnitude of the charge into the separation, this one, and it is always see, electric dipole moment always act from negative to positive. So that's why direction will be, electric dipole moment direction will be this way. So 2aq, this is electric dipole, and which direction it is working, negative to positive. All right, so this is 2aq. This has magnitude as well as direction, which direction it is working, negative to positive direction. So this is magnitude and negative to positive direction. Okay, negative to positive direction, the direction of the dipole moment will be, so here it is shown. All right, so this is, see, this is, so dipole magnitude of the dipole moment is actually the magnitude of magnitude magnitude of a charge of a charge, a single charge. Okay, there is a pair, right? So there you have to take only one charge into the distance of separation. Distance of separation between them, between the charges. Okay, so this is actually dipole moment. So dipole moment is actually a vector. So what is the net charge on an electric dipole? So net charge is always zero because you have plus or minus q, same charge. Okay, let us go to the next. Now, if we keep an electric dipole, if we keep an electric dipole near or inside a uniform electric field, then what happens to that? We'll just see that. Okay, so what we'll see now, we'll see what happens if we keep an electric dipole in a uniform electric field. Okay, so here you can see this is an electric dipole which is kept inside an uniform electric field. You can see uniform electric field is denoted by equidistant parallel lines. So these are equidistant parallel lines. Okay, these are equidistant parallel lines. So electric dipole is kept in a uniform electric field. And see this electric field, when we have a positive charge in an electric field will actually exert a force on this positive charge. And what is the magnitude of the force? That is q into e. This is due to positive charge, like on positive charge due to electric field. And similarly, on negative charge also it will exert a force, that is minus f minus q. And see, if I draw the force here, see, electric dipole always attract the, electric field always attract the positive charge and repel the, so this is actually positive q e, and see in this direction it will be repelling the negative charges, or the force will be in the opposite direction. Okay, see there is a minus sign over here, there is a positive sign here. So positive force, so electric force on a positive charge will be along the direction of the electric field itself, and this will be in the opposite direction. Okay, this one. Now you might be thinking, that whether these two forces will constitute equilibrium for this dipole, so that there will be no force acting on it. Actually, these two forces cannot establish any equilibrium. Why? Because see, this force, line of action of this force is this way, and line of action of force QE is this way. So they are actually not in the same line. So if I have force like this, then they will cancel each other if both are equal opposite. But if suppose both are equal and opposite, but their action, line of action, see this has line of action this way and this has this way. So they anyway they cannot cancel each other. They cannot okay, they cannot cancel each other. So what happens to this case? This case actually there will be no net force also. There will be net torque. Net torque. There will be net torque. What is the torque? What is the torque? So torque is actually defined as the force, one of the force or magnitude of one of the force into the distance or perpendicular distance, I should say, perpendicular distance between the line of action of forces. Perpendicular distance. Perpendicular distance between the line of action. Line of action of force. So look here in this case. So what are the line of action? I'll just draw once again. Let me just clean this portion. So in this case, line of action is in this direction. See along this line of action of forces, and this is like this. So this line of action of forces are also parallel to each other. So I have to find out perpendicular distance. So this will be actually perpendicular distance between them. I'm sorry. So this distance, this is, see this one. This one will be perpendicular distance between the line of action of the forces. Suppose this angle is theta. Then if this angle is theta, see then what happens? If this angle is theta, this angle is also theta, right? If the distance, if the distance, see if the distance is actually, see I can actually draw this also, like this I can draw. So this is also theta. Okay, this is also theta. I'm drawing parallel line with this. So this is theta. So ultimately what I have, this point, like this I have got. So I need to find out this one. So this angle, see, since this is actually this length, this has got length 2a, so we'll get perpendicular distance, this one, this as 2a, perpendicular distance will be 2a sin theta, because this is anyway, this is, see this is a because 2a is the whole length, so this is a, this will give you a sin theta, and this also will be a sin theta. So both will be actually 2a sin theta. 2a sin theta. Okay, this is the perpendicular distance, and what is the magnitude of force to QE? Okay, so I'll just write it here. You can see that what will be the dipole. This is 2aq into E sin theta. So what is 2aq? 2aq is p. P is sine theta. That means what? P is sine theta means P cross E. So this P cross E is the torque. So P is sine theta, that is P cross E is actually torque, tau. Okay, this is electric torque. So what is the role of this torque? See, in case of translational motion, we have force, that is the cause of motion. So similarly, in case of rotational motion, the torque is the cause of rotation or rotational motion. Torque is the cause of sorry, uh, this P is sine theta. Torque is P sine theta. It actually is responsible for rotational motion. Okay, if we see here, if the dipole is actually rotated by, see, generally what will happen? Torque will be like this. Sorry, dipole will be like this. But if it is rotated by angle theta, as you see here, it is rotated angle by angle theta. Excuse me. So dipole is rotated by an angle theta. So what is the work done in this case? See, work done dw is actually, see, work done means force into displacement. So here actually it is t into d theta. T means what? And d theta means what? D theta means actually small angle, and T is the torque. So we have to actually apply an external force to act exactly against this torque. Okay, so work done against torque. Okay, so what is torque? Torque we have seen. See, if I want to calculate the total dipole moment. So this is P sine theta d theta. So P sine theta d theta. So P, if we take common, this will be cos of theta. If I take limit theta 0 to theta 1, theta 0 to minus theta 1. Okay, sorry. We will take cos of theta 0 to theta line. So it will be cos of, so sine theta, there will be a minus sign here while doing the integration. So cos theta 1. So if I take common, so cos theta, actually cos theta 1 minus cos theta 0. This is the work done. Now PE, so this is the work done. Okay, this is the work done. All right, so this could be actually correlated to potential. This could be related to potential energy as well. So how to do that? See, potential energy is actually, see, potential energy U theta or work done is equal to change in the potential energy. So U theta could be written as cos of, see here, cos of theta 0 minus cos of theta 1. Theta 0, if I write that theta 0 to theta 2 to theta cos of theta 1. Okay, so this is, so this potential energy could be chosen like position, this theta 2 could be chosen in such a way that the potential energy will be 0 at the reference point. So reference is generally chosen as theta 2 is equal to pi by 2. So potential energy generally, the expression for potential energy, and theta 1, let us say that is theta. So that is generally PE minus PE cos of theta. So this is actually potential energy. Okay, potential energy, or in terms of vector we can write P dot E. P is the dipole moment and E is the electric field. Okay. All right. So we'll just move on to the point where we are. Okay. So here electric potential. We'll find out electric potential due to an electric dipole. Electric dipole. Electric potential created by an electric dipole. So here you look, this is the dipole, electric dipole, and I am trying to calculate electric potential at this position P, any arbitrary position P. So electric potential, what do we know about electric potential? So here see, to calculate electric potential due to this dipole, we need to find out electric potential for individual charges, like see V plus Q, V minus Q at this particular position P. Individually we have to find out. So what is this due to plus Q? Look, this one. And what is the distance between this P and this charge? So we can write Q by 4 pi epsilon naught R1. What about this electric field due to this point as negative charge? So it will be minus Q by 4 pi epsilon naught R2. Okay. Now what will be the net potential at this position? So there will be addition. Okay. So net potential at P will be Q by 4 pi epsilon naught 1 by R1 minus 1 by R2. Other things are same. Okay. Now we have to see what is this R1 and R2. See R1, if I go with vector, like see this is R1, this is R, and this is A, and the angle between them is, see I have to find out angle between A and R. See A is this way. Excuse me. We know from triangular rule, you can find this out. See, so R1 square will be R square plus A square minus 2AR cos of theta. Similarly, R2 will be R square plus this plus 2AR cos of theta. Okay, now what we can do, we can write what is 1 by r. So how to find out that? To find out 1 by r, let us write 1 by r square, r1 square. So 1 by r1 square, if we want to find out, see what we have got. First of all, let me write what is r1 square. R1 square is r square plus a square minus 2a r cos theta minus 2a r cos theta. Okay, so if I take r square common, this is 1 plus a square by r square minus 2ar cos of theta and divided by r square, right? So it will be a by r. So I am just taking an assumption that this r is much greater than a. That means this distance is much greater than the separation between the charges or the dimension of the dipole. So in this case, this term could be neglected. So what we get? We get r square 1 minus 2a by r cos of theta. Similarly, for r2 square also we can find out. Okay, let me just do one thing here further. So 1 by r, or let me write it here. What is then r1? R1 is r, and this will be 1 minus 2a by r cos of theta whole to the power half. Whole to the power half. So if I want to find out what is 1 by r, then it is 1 by r into 1 minus 2a by r cos of theta whole to the power minus half. Now if we take approximation up to first term, then 1 by r, this will be 1 plus 2a by 2r cos of theta. That means you get 2 get cancelled. So you get r plus a cos of theta. So this is what we get. Oh, I'm sorry. So what we get, I'll write a by r cos theta. Okay, that means you get 1 by r plus a by r square cos of theta. Okay. Similarly, if we do such calculation for see for r2, I'll write directly what I am going to get for the same approximation. So this will be positive anyway. So if we take r square common, this is r2. So if I take r square common, then see here will be 1 a square by r square plus 2a by r cos of theta. Okay, then this term could be neglected, so we get nearly. So I'll just directly go with r. So directly r2 will be r whole to the power 1 plus 2a by r of cos theta whole to the power half. Okay, so this if I want to write 1 by r2, so what will be 1 by r2? 1 by r, and this will be 1 minus a by r cos of theta. Okay, so this will be 1 over r minus a by r square, into cos theta. Okay, so these are the terms we have got. These are the terms we have got. So now if we put it here, so what is the value we are going to get? Q by 4 pi epsilon naught. See 1 over 1 by r. 1 over 1 by r was 1 by r plus a by r square cos theta. 1 by r plus a by r square cos of theta. What about r2? So that was like this, and here it was minus, this will be plus. Okay, so you get, see, this is 0, this is 0, so this will be actually 2a by r square cos of theta into the previous one, q by 4 pi epsilon naught. Now what is 2aq? So 2aq will be p, so p cos theta by 4 pi epsilon naught r square. Okay, so p cos theta by 4 pi epsilon naught r square will be the potential. I can just write it somewhere. Let me write it here. Okay, so we have got v is equal to q by 4 pi epsilon naught. So here was 2a cos of theta by r square. So 2aq will be p cos of theta divided by 4 pi epsilon naught like this. Okay, so this will be the case. So this could be written in terms of unit vector also. See, p is the vector quantity, and if we take the r cap in which direction? In the direction of dipole itself. So p dot r cap. So p dot r cap 4 pi epsilon naught r square. Okay, or in other word, if we do this, p r cube okay. So if you know, if this is the case when actually r is much greater than the dimension of the dipole itself. Okay, okay, so you can see the simple difference between the electric potential created by a point charge. So that was what? That was actually q by 4 pi epsilon naught r, but now we are getting for a dipole it is r square. See, for a dipole electric potential is varying as r square. Okay, so this is for point charge. Sorry, for this it is varies as what? Sorry, r square potential itself. Potential varies as r square, so slope is much, and this is directly proportional to, sorry, inversely proportional to r. If this is voltage, so I'm sorry. This side is distance. Okay, distance. All right, so I think I'll stop it here. Next day, what we'll do, we'll take up electric field produced by dipole and related numerical problems as well. We'll discuss. Okay, so thank you for your patience. Bye for today.